Martin Rowe with EE World. We are at day 2 of OFC in San Diego. This is the Optical Internetworking Forum booth, and we have lots of demonstrations here about interoperability. And this particular one, this whole table that you're looking at, talks about mostly about co-packaging. And Jeff Hutchins here is going to explain this demo about energy efficiency. So Jeff, why don't you tell us what we're looking at here?
Okay. Yeah, so what we have is the energy efficient interface demo. This is a static demo to talk about the next generation of what we'd expect to do for back-end compute in the data center. This chart here I like because it shows the front-end Ethernet, shows the back-end connection for scale out, and it shows the connectivity within the GPU clusters for scale out.
So what we're looking at here is a diagram of the equipment that's shown on the table.
Well, shown in the table, but this diagram here is really meant to show the different kinds of links that we need to look at for making the back-end compute energy efficient.
Okay.
And you'll see there's the orange links in here, which are PCIe-like type links. There's also a green link, which is low latency Ethernet, low power Ethernet, and then there's the standard front-end links here, which are in blue.
Okay.
And then if I grab this one here, this diagram, then goes in and shows how these different links come in. You can see there's the compute to I/O, compute to memory, compute to local compute, compute to remote compute, and these are all low latency interfaces we use for the back end, and you'll see some specifications. At the bottom are the kinds of standards people are using today. So you see the standard InfiniBand, NVLink, UEC and CXL and all that stuff. Yeah, so those are all the different interfaces. And the goal here, when we do AI computation, is these problems are broken up into tiles, and there's lots and lots of parameters, and all that data has to be moved between the various GPUs because you don't finish a calculation until all of it's done for a particular section. So the goal, and so the time of flight, the latency and the SerDes, and all those factors affect how fast you can get things done. So we're looking at the interfaces between the GPUs and how we can make them more efficient. And when you make them close together to get the latency down, you also have to worry about power, because power consumption turns into a thermal problem.
Yes.
So by making these more energy efficient, we do that. So in this section here, we're showing the next generation link. I'd start with this thing in the center. So this is a mock-up, but it's meant to convey where we're headed. This grayscale here represents an ASIC, and what we've done is put optical engines co-packaged with this ASIC. Each of these is meant to represent about 4 T of bandwidth. So that's 6 times 4 is 24 T total bandwidth.
So that's 24 terabits per second.
Terabits per second.
For all of these links, yeah.
Right, for links and something like that. And it shows you the size. So the bandwidth edge density here is about 1 T per millimeter. We also have some optical NICs on either side to reach out, and HBM memory in the back. Over here you see an example of a front-end NIC card, again co-package integrated with an optical engine on the side and the ASIC there. And then this is just for reference as a CPU socket, as we'd have today. And you can see the optical engine powered up by external laser source.
Okay, we're on the other side of the table, and what we're looking at here is 4 different demonstrations relating to ELSFP. And Jeff is going to explain what the goals of this project has been.
Yeah, so a few years ago, we worked with some of the hyperscalers, Meta and Microsoft, to look at what we do for next generation Ethernet switches. And with that, we created a couple agreements, and one of them was the ELSFP, and I'll just show a diagram of it here. What's unique about this is it's a pluggable optic, but the optical connection is made at the rear of the module. That's important because there's high powers and you want to be eye safe, so you want to make sure that there's no way someone could get exposed to it. So when you plug it in, it powers up and light goes out the back end into the system and powers the co-package switch.
So does it first make the electrical connections before it makes the optical connection? Or is the optics or is the laser already on?
No, the laser can't be on until it's powered up, but I imagine there's a time delay by the time the power is put on before the the internal electronics catches up and starts driving the laser.
So that ensures that when you plug it in, the laser is not active.
Right.
And then only when it's plugged in does the laser become active.
That's
Therefore,
right.
you can't see it. You can't look at it directly.
That's right.
Okay.
That's right. And so what we're showing here today is the ecosystem is really expanded. We have 4 different companies. Output powers are in the range of 20 dBm and 23 dBm, so fairly high power lasers that we use for co-packaging. On this side over here, one of the important things inside of the when you plug these things in is to make sure the blind mate connector is clean and what it looks like. And this is just an example of the ecosystem responding with an inspection system to make sure this unique blind mate connector is clean and good to plug into the system.
Okay.